Previously, we've been looking at measuring current, and to do that, we used an ammeter, like that. And current was a measure of how much charge flows around a circuit. So we know that conductors have things like electrons, and the electrons in metals and conductors are free, and they can move around a circuit. And as they do so, that's what causes current. We know that electrons are negatively charged, and the current is really this flow of electrons flowing away from the negative terminal of a battery or a cell around a circuit back into the positive. However, we say that current actually flows from positive to negative. Well, what else do we need for a current to flow? If I just got a bulb, no current flows through it. If I connected a wire from one side to the other, still no current flows, obviously. What do we need? We need some sort of power supply, like a battery. And a battery provides what we call a voltage. And voltage is what I want to think about today. So in your notes, a battery is a device in which chemical energy, chemicals inside it, is converted into electrical energy. And if you look at any particular battery, somewhere around it'll have a number saying its voltage. In this case, this is 1.5 volts. And a voltage is a measure of how much electrical energy is provided to a bit of charge when it flows through a cell. So an AA battery or a D cell like this one, they'll be 1.5 volts. Sort of rectangular ones that go in smoke alarms, they'll be 9 volts. A car battery might be 12 volts. And so the bigger the voltage, the more push really there is to the electrons. So the voltage of the cell is a measure of how much energy is transferred from the cell when a unit of charge passes through it. And we measure voltage in a unit called the volt, which we shorten to a capital V. So as I said, a current is measured using an ammeter. Voltage is measured using a voltmeter. And you can see they look very similar. In fact, in school it's very easy to get mixed up between the two. If you ever do have to use them, make sure that you see which one says A for measuring amps, an ammeter, current, and V for measuring volts. We can also use a multimeter set up as a voltmeter, and that's what we're going to use today to measure voltage. So it's a bit easier for you to see on screen. So voltage is measured using a voltmeter. Please note whenever you're spelling things like ammeter or voltmeter, it's METER as opposed to METRE, which is our unit of length. Now, one big difference between an ammeter and a voltmeter is the way you connect them. Ammeters are to be connected in series with whatever you're measuring the current. So you break the circuit and you put the ammeter in series, whereas a voltmeter must be connected in parallel. And we'll have a look at how that goes today. So a voltmeter measures what we call a potential difference. It measures the difference in energy from one point to another point in the circuit. So it needs to be connected in at 2 points. So what we're going to do is we're going to measure the voltage of each of these cells individually, and then we're going to combine them together in different circuits and see what happens to voltage whenever we add cells in different ways. So to do this, we're going to label each of these 3 cells A, B, and C. And that's just so we can keep track of them. So I've got this set up as a voltmeter here. The black wire needs to be connected to the negative side and the red wire needs to be connected to the positive side. So let's see what we get. So for A, getting 1.53, and I'll record that on my notes. For B, very similar, got 1.55 volts. And for C, 1.57 volts. Remember I showed you that these are 1.5 volt cells. We see we're getting about 1.5 volts. So those are the numbers that we'd expect. As a battery runs out, it'll tend to get a lower and lower voltage. So what we have to do now is connect the cells in different ways and record the voltage. So firstly, we need A in parallel with B. And then we measure the voltage across A and B in parallel. And we get 1.53 volts. Let's record that. Right. Now, A and B in series. Now we've got an increase in voltage, 3.09 volts. Now A and B in series, but with the two negatives facing one another. And the voltage has gone way down, 0.02 volts. Now all three in series. Let's put that the right way. What's bigger voltage? 4.66 volts. So what do we think's happened? Here, when we had A and B in parallel, the voltage didn't seem to increase at all. In fact, it's the same as the smaller voltage. So what we can see is that in parallel, voltages do not add up. Voltages remain the same in parallel. With A and B in series, we've got 3.09 volts, and if we think 1.53 plus 1.55, that will come up 3.08, which is pretty much the same as 3.09. There's a rounding difference there. So whenever we add two cells in series, we can see that the voltage adds up. And similarly, remember back when we measured current, we saw that if we turned one cell round, the bulb went out. That's because the voltages subtract from one another in this case. We have 1.55 take away 1.53, leaving 0.02. So whenever we connect cells the wrong way around, the voltages cancel each other out. Essentially, the cells one cell pushes the electrons in one direction, the other one pushes in the other direction. Finally, when we have three cells all in series, they're all going to add up to one another. So 4.66 is, well, if we have 1.53 plus 1.55, that's 3.08, plus 1.57, that's going to be 4.65, which 4.66 again, there's a rounding difference there. So we can see that in series, voltages add up. So, top of page 26 in your notes, it asks you to try to predict the reading of the combination cells A, B, and C in the circuit below. So we have A plus B the right way around, and C turned the wrong way around. So what do you think the voltage is going to be? So we have A is positive, then negative, B positive and negative, and C negative and positive. I'll let you think. You can pause here, try and work out what you think it's going to be, and then we'll see. And we've got about 1.52 volts. Now, why is that? A, we had 1.53. For B, we had 1.55. So we add those together, we get 3.08. And then we can take away C, 1.57. And that gives us 1.51. We've got 1.52. Again, just a rounding difference in our meter. So we can see that as we add voltages, so add cells, the voltage increases. Turn a cell around, the voltage will decrease. And that's going to be something like our conclusion here. In order to help each other, cells should be connected positive to negative. Adding cells in series increases the total voltage. Adding them in parallel does not increase the voltage. Is there any advantage to adding cells in parallel? Doesn't increase the voltage, so it wouldn't make a bulb any brighter. I'll show you that now. I got a single bulb and connected that to a single cell. We can see it turns on fairly dimly. What happens if we add a cell in parallel? Is it going to get any brighter? No, it doesn't. The voltage doesn't increase. So is there any advantage to using a system like this? Well, the one advantage is the batteries will last longer. So that's going to be one particular advantage. It'll make a battery last longer, but won't increase the voltage, so it will not increase the brightness. One thing that is interesting is that if you measure the voltage across a cell, we can see in this case 1.53 volts, and then we add a bulb, I want you to notice what happens whenever we plug this in. So I've got 1.52 volts. It actually drops down to 1.49 volts. The voltage sags a little bit. And that's to do with whenever a current flows, as there is now, a little bit of energy gets lost inside the cell. You know that if you put current through a wire, it heats up a little bit. That's how a bulb works. It makes a little wire glow white hot. Well, it'll cause the cell to heat up a little bit as well. And so some of the energy gets lost inside the cell. There's what's known as an internal resistance inside that. That's not something you have to worry about too much. So in summary, that's how a cell works. It provides it stores chemical energy, it provides electrical energy, and it pushes the electrons around the circuit. So when a cell is connected to some lamps, the voltage of the cell pushes electrons around the circuit. And the energy to do this comes from the chemical energy of the cell. That pushes the electrons around, and that is what electrical energy is. So in this case, the chemical energy is turned into electrical energy. And the electrons, whenever they pass through something like a bulb or a motor, they give up that electrical energy. So in a bulb, they give up the electrical energy to the thin wires inside the lamp. And that creates heat, which creates light, so it makes the bulb light up. So far, we've measured voltage across the cells. But we can measure voltage at any point around a circuit. So if I set up a very simple circuit again, I'll draw a bulb lit up. Whenever we connected our voltmeter into the cell, we were really measuring the voltage in, the amount of electrical energy per unit charge being put into the circuit. But a bulb is going to take the energy out again, and we can use a voltmeter to measure the voltage out. Here we're getting about 1.48 volts, which is what we had the last time, 1.49. So the amount of energy going into the circuit, which is measured by voltage really, is going to equal the voltage out. So across each lamp there is also a voltage. It's measured in volts too, and it's a measure of how much electrical energy is taken from a unit of charge. Let's see what happens if we've got a circuit with several things in it. So now I've got a very simple circuit with 2 cells and 2 bulbs. And this is the circuit on page 27 in your notes. So connect 2 cells to 2 lamps in series as shown in the diagram. Then connect a suitable voltmeter across one of the lamps as shown here. So we can see that we can see that our voltmeter needs to be connected in parallel to the lamp. We say we measured the voltage across a lamp. There we go, and we're getting a reading of 1.46 volts. Now, reconnect the voltmeter across the second lamp, and that's going to be V2. In this case, we're getting 1.47 volts. Then it says use our voltmeter to find the voltage across the battery, which is both cells together. So to do that, I need to connect it into these terminals so it's across the whole battery. We're getting 2.94 volts. So let's have a look at these three readings. 1.46, 1.47 and 2.49. Is there any pattern here? 1.46 plus 1.47 equals, 2.93, 2.94. They're the same answer. Again, we're just getting slight rounding differences whenever we use a meter like this. So we can see that the 2.94, that was the voltage in. This took 1.46 volts. This took 1.47 volts. In other words, the total voltage in was shared pretty evenly by the two things coming out. So the total voltage in equals the total voltage out. If I took one bulb out and plugged it in, what would we expect to happen to the brightness of the bulb? It should be brighter. Now, why is it brighter? Again, we've still got the 2.9, roughly 2.9 volts going in. Well, what's the voltage coming out? There you go, we've got that 2.9 volts coming out. So this time it's brighter because it doesn't have to share the voltage. It's taking all the voltage itself. All the energy that's being put in by the cells is being taken out by the bulb. That's why when we increase the number of cells in series, we get a brighter bulb because we're having a bigger voltage. It's also why we get a dimmer bulb whenever we add bulbs in series, because the total available voltage is being shared out among all the bulbs. So the more bulbs there are in series, the dimmer the bulb's going to be. So in summary, what do we notice about our three readings? In a series circuit, the sum of the voltages across the individual components, in other words, across all the bulbs or whatever it is, taking the voltage out, equals the voltage across the battery, equals the input voltage. And we can write that down as a little simple equation. So V, which is our input voltage, equals V1 plus V2 plus V3. That's all our output voltages, and so on. What happens if we start adding things in parallel? So in the box below, draw a parallel circuit with 3 cells in series and 3 bulbs in parallel with each other. There are 3 cells in series. You should be using a ruler for this. And we need 3 bulbs in parallel. Okay, so let's build this circuit and see what it looks like. So here are 3 bulbs in parallel, or 3 cells in series. And we can see that the bulbs light up quite brightly. Now for V1, it says record the add in a voltmeter across one of the 3 bulbs. So I'm going to measure a voltmeter across this top bulb. And I'm getting a voltage of about 3.97 volts. That's connected across the second bulb. That's very similar, a little bit lower, 3.3. say about 3.80. And again, across the third bulb, in this case 3.84. So we're getting three very similar readings. Then use the voltmeter to find the voltage across the battery. It says both cells together, should say all three cells together. We're getting the roughly about 3.93. What do we notice about these three readings? Well, they're all very similar. They're all pretty much the same. We can see these are flickering occasionally. I think we've got just a bit of a loose connection occasionally, which causes the voltage to flicker a little bit. But we can see that in parallel, the voltages were all pretty much the same, and they're all the same as the input voltage. So by adding things in parallel, we get the same voltage each time. So in a parallel circuit, the voltage across each component equals the voltage across the battery. And components in parallel always have the same voltage. So we could write that down as so V, which is our input voltage, equals V1, which equals V2, which equals V3. The voltage stays the same. Does that mean I could just keep adding bulbs on forever and keep it working brightly? No. As we add more bulbs on, eventually more and more current will be drawn from the cells and the voltage will sag and they won't be able to sustain that current. One major advantage of this is if I disconnect one bulb, the others stay on. So I'm not relying on each bulb being perfect to make sure the rest work. Disadvantage is it'll drain the batteries much more quickly. So let's have a look at a summary of this. If we compare current and voltage in series and parallel, what do we remember about current around a circuit? Well, in series, the current is the same at all points. What happens to current in parallel? Well, in parallel, the current will split up down each individual branch. But at the end of each branch, the current will join back up together again. And what do we see today in voltage? Well, in series, the voltage is shared out among components in series. And what about voltage in parallel? Well, the voltage of everything in parallel is the same.